Today we begin with Unit 4, which is mostly about vector-valued functions. In this first section, we're looking at arc length and curvature. These learning objectives are good to look at to determine the length of a particle's path in space by using the arc length function. So we should be able to explain the meaning of the curvature of a curve in space and state its formula. Most of this section comes straight out of the textbook, which you already have access to. I'm not going to spend too much time reading over these paragraphs, but this first one is a good one to read just to give you an idea of how we can use arc length and curvature. Let's say if we have a vector value function and that function describes the motion of a particle in space. We could determine how far the particle has traveled over a given time interval, which can be described by the arc length of the path it follows. Say that we have a road that we're trying to build, and we want to determine how sharply the road curves at a given point. This is called the curvature. First up is the arc length formulas. And notice that the simplified version of these two formulas is exactly the same. It's the integral from a to b of the magnitude of r prime of t dt. What this tells us is that the arc length is equal to the integral of the magnitude of r prime. I'll work out example 1 below. This says calculate the arc length of a parameterized curve. So as we wrote before, the arc length is equal to the integral of the magnitude of r prime. Let's start by finding r prime of t. Derivative of 2t squared plus 1 is 4t. The derivative of 2t squared minus 1 is also 4t. And then the derivative of t cubed is 3t squared. Now we can find the magnitude. The magnitude of a vector value function is just the square root of each component squared. So then we have the square root. 4t squared would be 16t squared. And then we have another 4t squared, so that's 16t squared. And then 3t squared squared is 9t to the fourth. That would be 16t squared plus 16t squared is 32t squared plus 9t to the fourth. Let's factor out a t squared. We'd be left with 32 plus 9t squared. Since we factored out the t squared, we can take the square root of that factor. So that would come out as a t. And then we have radical 32 plus 9t squared. Finally, we can find the integral from 0 to 3 of our magnitude of the derivative. So that would be t radical 32 plus 9t squared dt. In order to solve this, we're going to have to use u substitution. I'm going to let u equal what's inside of the radical, 32 plus 9t squared. If I take the derivative of both sides, I'd have du dx, du dt is equal to 18t. Multiply the dt over to the other side, and we would get du is equal to 18t dt. And then we can get the dt by itself by dividing both sides by 18t. That leaves us with du over 18t is equal to dt. So then our integral, we have a t on the outside, we have radical u, and then the dt can be replaced with du over 18t. Let's change our boundaries. The top and bottom boundary over here were in terms of t. We now want to transform those in terms of u. So for t equals 0, we can plug that value into the u formula. So we would have u is equal to 32 plus 9 times 0 squared. That would give us 32. So the bottom boundary of our integral is 32 in terms of our upper boundary was t equals 3. Let's plug t equals 3 into the u formula. That would be 32 plus 9 times 3 squared. 3 squared is 9. 9 times 9 is 81. 32 plus 81 is 113. So our upper boundary here is 113. We have a t in front of the radical u. We also have a t in the denominator here. So those t's will cancel out. And this 18 that's in the denominator, we can move that out front of the radical as a coefficient. That means our integral is 1/18. The integral from 32 to 113 of radical u du. I'm going to rewrite this radical as being a 1/2 exponent. 1/18 antiderivative of u to the 1/2 would be 2/3 u to the 3/2. And our boundaries on that are 32 and 113. I'm going to pull this 2/3 out front and multiply it with the 1/18. So we'll have 1/18 times 2/3. And then I have u to the 3/2, so that'd be 113 raised to the 3/2 minus 32 raised to the 3/2. From here, we're going to get decimals no matter what we do. So I'm just going to throw all this in the calculator. And then this is equal to 37.785. So to calculate the arc length of a vectored value function, we first found the derivative of the vectored value function, then found the magnitude of the derivative, and then we did our integral. From here, in order to evaluate this integral, we had to use u substitution. Once we had our antiderivative and our boundaries set up, we just threw all that in the calculator, and that gave us our final answer of 37.785. Try example 2 on your own. I'll show you my solution in the next video.